Thank you so much, Mark. And it's a great pleasure to be with you all today and share with you kind of a different take on underwater archaeology and how we're applying many of the techniques that all of you have developed and created over the many years. And we're just taking it into really a very different environment, which are the flooded caves of Quintana Roo, Mexico. And so basically my presentation today is an overview of what we're doing using a recent discovery of ours as, I guess you would say, a case study in how we do what we do in this very different environment. So let's see if I can get my, here we go. I am, of course, speaking to you from Mexico right now. Buenos dias. It's morning here. And I am speaking as the director of CINDAQ, the Centro Investigador del Sistema Acuífero de Quintana Roo. We're a Mexico-based nonprofit. I'm speaking on behalf of my colleagues and friends, Fred DeVos, Chris Lamayo, Julian Fortin, and Daniel Ponce. Of course, all of them are out diving right now. So I'm back in the office. And we have had almost a 20-year collaboration with the National Institute of Anthropology and History and their underwater archaeology division, originally under the directorship of the late Pilar Luna, and now under that of Roberto Junco and Elena Barba. As I think Chris Underwood mentioned in the 50 years presentation, we have recently become an accredited NGO with UNESCO in the protection of underwater cultural heritage, something we're very proud of. And actually our relationship with NAS goes back to 2010 when Ina sponsored a course for us and Chris came here. And we began with the basic NAS course, and last year Chris, Fred, and I were all given the award in maritime archaeology through the work that we've done here. So our mission, as it states here, is to facilitate the research and promote education and support the conservation of both natural and cultural resources associated with the cenotes and underground rivers of the state of Quintana Roo, Mexico. And I'll add that on the feed loop booth that we have, there are links to all of our social media, our websites. I've put some of the publications that I'll be referencing, one of our annual reports, and there's actually a video there as well for your reference. And I'm going to be hanging around in the booth afterwards should any of you have any questions at all. So I always like to start with a basic geography lesson, and we are based on Mexico's Yucatan Peninsula here. And really in the context of what we're speaking about today, the most important thing for you to realize is that this is an enormous limestone platform. The platform actually extends up into the Gulf of Mexico here. It's now submerged. And of course, because it's limestone, this area is riddled with solution cave systems. What is basically the keeper of data for this area, the Quintana Roo Speleological Survey, currently has officially 407 underwater caves and cave systems in its database of information, and over 1,600 kilometers of confirmed underwater data, and an additional 354 kilometers of dry cave passageway. So there's quite an extensive network of these cave systems, particularly on the eastern Caribbean coast where we're located here, really in the area of Tulum, which is a little bit south of where I'm speaking to you all from today. So, of course, the caves of this area were all dry during the last ice age, and water levels worldwide during the last ice age were approximately 120 meters lower. So this whole area that's now submerged out into the north of the peninsula would have been exposed and habitable during that time. And so you might ask, how do we know that these caves were dry? Well, there's several factors at play. One of them is the fact that within the cave systems themselves, we find speleothems, stalactites and stalagmites in these now submerged cave systems that could only have formed in an air environment. And so that's one of the kind of proofs that we have that these caves were dry at some point in time. The other is in the human record within them and the animal record within them. And paleontologically speaking, the Yucatan Peninsula is an incredibly rich emerging site for a lot of studies, not only with the ancient Maya civilization, but going back into prehistoric times. And we're going to be focusing on, with the site that I'll speak about today, is more in prehistoric times. So again, proof that these caves were dry. These are 7 of the actually 10 human skeletons that have now been found and identified within our cave systems here. As you can see, they are fairly well preserved, in many cases very much intact, and they are an incredible resource to help scientists understand the peopling of the Americas. So, of course, humanity spread across the planet, and the Americas is one of the last frontiers for early humans. And there are competing theories and ideas about how people got here and when they got here, and still many questions that need to be answered. There is definitely no doubt that humans came across the Bering Land Bridge. And in the case of Naya, one of the skeletons from here, from the Hoyo Negro site, she has her DNA traces her basically back to Siberia, proving that link. So the caves of this area, again, are just this incredibly rich playground for paleontology and archaeology, and helping us answer many of these questions. So one of the questions we've always had here is, why did Paleo Indians enter into the caves of Quintana Roo? And you can, from the beginning of humanity, caves have played an important role and factor in human activity. And certainly caves provide shelter. In our case here, they perhaps could have provided some resource of water, since the water table was lower, and so people might have had to venture into the caves to find freshwater resources. But there was never, we had always seen proof of them having been there only in their remains. We've never ever seen real physical proof of them being there. So what this then leads into is a discovery we made in 2017. And so basically what we're going to be speaking about today is all contained with a cave system called the Sagittario Cave System. This is my colleague Fred DeVos here, and Fred teaches a cave survey class. And so this cave was originally registered by INA in 2016, and the original explorers told Fred about it and said that it would be a great place for him to go and conduct a cave survey class. So that's exactly what Fred did. And in the process of doing that, his students went off the line to measure a sidewall distance and came across a passageway that the original explorers had missed. And so our effort to begin mapping this and exploring it started in 2017. And from the original, I think it was about 2,000 meters of original exploration, we were able to expand it by more than 6 kilometers to its present length of approximately 8,800 meters, which may sound like a large cave, but in the relative scale of things here, just to the south of us in the Tulum area, we have Sistema Sakatun and Sistema Uxbelha. And just kind of as a matter of scale, each one of those is now approaching close to 400,000 meters of cave. So Sagittario on the relative scale for us is not a huge cave system. And so Fred and I did the first exploration dive into Sagittario, and basically we started immediately to see that things were slightly amiss in this cave, if you will. And so over here on this large, this is an actual screen grab of a three-dimensional photogrammetric model we made. And this is the exact spot where we really just started to scratch our heads. And what you can see, this is a 50-centimeter scale right here. And you can see along this edge here, it's just very clearly broken all the way along the extent of it here. And that you have tailings piled up behind here. So this floor was broken, and then the floor was piled up. The broken pieces of it were piled up behind. And you can see the pigment on the back side, the underside of the rock is very iron rich. And so this appeared to us not to be a natural occurrence, but more human activity. And the more we looked around, we started to see things like this. This is a broken speleothem that would have been used as a hammerstone to actually do the breaking of the floor. We also came across, as you can see here, rock cairns marking the passageway through the cave. And so we obviously noted all of these things and reported to the National Institute of Anthropology and History. I've got a short video here that just kind of shows you exactly the same, more of the same stuff here, but you can see the breakage along here. You can see tailings rocks piled up here. Again, you can see kind of iron rich sediment discoloration down through here. And this is pretty thick stuff that people had to break through. So you know, immediately what we're seeing is that there was a tremendous amount of effort involved in going into here. So the question is, well, why were people going through all of this effort? And what happened is what we set in motion was a study that was published last year in Science Advances. And again, that publication is there in our booth for you to download. I'm not really going to get into the results of the publication, but the overall takeaway is what they were looking for was ochre. And the ochre, Dr. Brandy McDonald of University of Missouri Columbia was brought in as the ochre expert for this project, and she did her analysis of the ochre, and it's extremely pure on the scale of ochre purity. So, of course, ochre's been extremely important with humans going back to 75 to 100,000 years ago in South Africa. There's evidence of human use of ochre, and of course that spread across the planet as humans migrated across the planet. So from our perspective as divers who are trained with the eyes of archaeologists, is how do we create a base of information that allows us to take non-diving scientists into a place otherwise they won't physically be able to go to. So first and foremost in that process is creating a map. And so this is just an outline of our basic standard operation procedures for creating a map. And that begins with survey. When we explore the caves here, we leave a thin nylon line through the middle of the passageway. And that is our safety guideline, but it's also what we measure to create basically the skeletal structure of the map. So we survey using a semi-automated tool called a NEMO that is extremely accurate and very, very efficient in terms of allowing us to do this work. And so you get kind of a stick map here. And what we also do is take left down upright measurements to get a volumetric idea of the size of the cave. And so you can see in this image here that the sidewall and floor to ceiling measurements are all now included in it. And then we come back to the surface with that information print it out on a gridded survey sheet, come back in, and then we do sketching of the cave, hand sketching of each section of the cave, which again is digitized, creating a much more pleasing image. And then of course, what we can do, as many of you do, is we can start to overlay the distribution of artifacts and cultural features, observations that we make on top of the map. And so for this project, just to give you an idea, we mapped the entire 8,855 meters of cave. It took 19 divers, approximately 100 dives, and approximately 600 cumulative hours of dive time, and then 50 hours of computer time. And we, as you can see here, we have underwater cave passage, we have dry cave passageway. And so the result was this map here. And so the map, as for many of you, of course, your sketches of shipwrecks, this is critical of putting everything into context and putting everything into space. The difference is that in nautical archaeology, a shipwreck just arbitrarily falls to the floor of the ocean, and the floor of the ocean probably isn't so much a part of the story. In our case, the cave is very much a part of the story, because we have to understand how these people, and in some cases prehistoric animals, got into these cave systems. So we have to put the entirety of the cave into space and then start to relate things. So this is a 50-meter scale here, and you can see we have the primary entrance. This is the primary entrance we get into, and then we came across two other entrances here. So we're fairly certain that people were accessing, the prehistoric people were accessing this area that was mined. You can see here, this is pretty much the most extensive part of the mine here. And there is, it's not just one little pit. This is several kilometers, representing 2,000 years of continuous resource extraction, and it's a fairly large site. So the map is really the foundation of everything, and at the very least, that is what we always strive to do with this type of project. And the following maps here, this is all derived from the map that we created, but of course, the map allows us to place our observations in this top map here. This is all from the publication. We can place any place that we took a sample. These are all charcoal samples. This is everywhere that we observed charcoal within the cave. In this instance here, everywhere that we saw open mining pits and mine spoils is related here. And then wherever we saw stone cairns, piles of rocks, and broken speleothems is all placed on the map here. So of course, this is extremely informative to the scientists we work with. And in here, just kind of a different take on the map, because we do the left, right, up, down measurements, it also gives us a cross-sectional view of the cave. And of course, with charcoal, we have to be very careful here not to assume that it's always brought in by humans. It's a natural process, and a lot of charcoal can naturally be washed into a cave. And so by having a cross-sectional map like this, it allowed us to see that because of certain restrictions in the cave and the area, this is the area where the mining took place, it would have been near impossible for anything to wash in here, and therefore that it must have been taken in by humans. And one of the interesting outcomes of this study was that the charcoal not only was used for carbon-14 dating to get our range of those 2,000 years of continuous exploitation of the cave, but it was also used, Dr. Barry Rock at the University of New Hampshire put the charcoal samples under a scanning electron microscope and was able to determine the specific species. And the three main species are known as torchwood and candlewood, and the other one's copal, but they're all extremely resinous and bright burning species of wood that seem to have been selected primarily for that purpose, for lighting the cave. So the map is extremely important in terms of orienting us and orienting the scientists and placing everything into space. We also use photogrammetry in the cave environment, and this is obvious to all of you, but of course it provides with incredible amount of site documentation, a baseline of information of how things appeared when originally found. It allows us again to take the non-diving scientists into the cave environment and do non-invasive research. It's a tremendous aid for us in dive planning, depending on the accuracy and the precision and the richness of the point cloud that we create. We can get down to the very pebble that we have to extract if needed. And for object recovery, it's an incredible tool. I'll show you an example in the next slide. And of course, it's an incredible educational tool to take not only the scientists, but the general public into these extremely fragile and important sites. So this is just a case of how great this technology is. And what you're looking at here in the upper right or upper left is a giant ground sloth skeleton from the Hoyo Negro project. This is about 55 meters deep in Hoyo Negro, which is an incredible place to see site that has human remains mixed with fauna and megafauna, both extant and extinct. And this is a Nohochi chak, which is a new species of giant ground sloth. And what's highlighted in red there is the pelvis. And so it was determined by Ina and the paleontological team led by Dr. Jim Chatters that the sloth pelvis needed to be extracted for the taxonomy and identification of this new species. And of course, a giant ground sloth skeleton that's been underwater for thousands of years and is A, large, and B, extremely fragile. So we couldn't just attach lift bags to it and bring it to the surface. And so what was done was that from the point cloud, and this is using software that I'm going to demonstrate for you in a second called Viscore, developed by the University of California, San Diego, Vid Petrovich. And we're able to extract whatever we want from a point cloud. And what they did here is did a reverse print of the ground sloth model derived the sloth pelvis derived from the point cloud. And here it is underwater. This was brought from 55 meters up and then swum through horizontal cave passageway, and it fit like a glove. So just a really, from my point of view, pretty cool use of point cloud technology and photogrammetry to recover an object. The tools we use, for large passageways, which I'm about to show you here, we use the Sony A7 Alpha series cameras and an Autocam housing and the Keldan lights, which are very, very nice, even light. We've also developed a methodology, and that's also in our booth for you to download if you want. We published a paper with the ISPRS on the use of the GoPro because in certain circumstances we have low ceilings and we can't fit the big camera rig in there. So we were forced to kind of experiment, and we came up with a pretty great system of doing photogrammetric models using GoPros as well for underwater sites. So what we're going to do now, I'm going to jump out of my PowerPoint presentation, but we're going to revisit this site right here. And what I did, give me just a second. So we're going to go here and to here. And what I'm doing is I'm opening up our, Mark, can you just confirm that everybody can see this here?
I can, yes, Sam.
Okay, so what we're looking at here, this is Viscore. This is the proprietary software, again, developed by at the Qualcomm Institute, University of California, San Diego. And this is the three-dimensional model we created of the mine site. This is approximately 250, 300 meters of cave passageway here that loops back on itself. And it was exemplary of the mining activity that we had seen. So we decided to model it. This took about 10 dives. There's, I think, 18,000 photographs were used to create this model. And the point cloud itself is 3.7 billion points, billion with a B. So we're going to come into the mine site here, and this is just so fantastic to be able to give anybody this opportunity to see this. And there are a number of tools that we have within Viscore that are pretty phenomenal. One of them, which I'm going to do right now, I can focus on any point within a cave. I'm going to pick a center point here, come over to ortho, and basically what I've done is created a cross section of the cave that I can bring up here. So you could imaginably do this with a shipwreck as well. And then I can determine how thick I want that cross section to be. So right now it's about, we'll make it a meter. So that's a meter thick. And then what I can do is I can scroll through the entire cave passageway here. And of course, for a site like this, if I turn on a grid, it allows us to be able to measure the depths of some of these mining pits and kind of get an idea volumetrically of how much material was actually being extracted. So a really incredible tool built into Viscore. Here you can see one of the rock cairns that we initially started to see. There's another one here. And I'm going to move down the passageway, more rock cairns here. And another tool that we have, as I mentioned with that ground sloth pelvis, is I can basically highlight things within the cave that I want to separate. So what I've done here just for this presentation is I've gone through, and everything in red here is an identifiable cairn marker through the center of the passageway. And so we have a brush tool here. It's very simple. I'll just demonstrate it here, but on this rock, I can highlight that rock right there and then separate it from the noise of the background. And what we can do here is I can then get rid of the noise from the background and we can start to see this. So imagine a cannon or human remains or whatever it is you find on a shipwreck. You have this capability as well. So Viscore is just an incredible tool for us and allows us to really create this digital twin and have the ability to take scientists in and allow them, without the fear of them having to cave dive, come into these sites and study them. And just to finish here, this is obvious kind of what we were seeing in the video I showed earlier of cave floor breakage and spoilage being piled up on top. So I'm going to get out of Viscore. And we're going to go back to PowerPoint. And that's just a, there's a link to our website. We have a whole thing. This is just a fly through of the model here. That's on our website, so you can kind of see that on your own after the presentation if you wish. The other thing that happened on this project, and this kind of just fell out of the sky, was we had the opportunity to demo a Boxfish 360 camera. This is a high resolution. It records in 6K 360 video. And so this was just another complement to everything else we had done. And so what I'm going to do here, and this is raw 360 imagery here, and I'm going to, takes it a second to pick up, but this is exactly the passageway that I just showed you the model of. And we went right by this group of rocks here in the rock cairn. And once it figures out it's a 360 video, which should be any second now, we can start moving around in the image. And so the model is good. It doesn't capture everything though. And so with a 360 video, obviously it doesn't miss anything. And so we can see the ceiling. You can see us pointing things out. I'll admit it's very nerve-wracking to swim one of these things because it doesn't miss anything. So we have to be extremely careful as we're going through. Otherwise, everybody will see it. So here's a mining pit right here. So again, just a complementary tool to the map. The photogrammetric model is this. So a scientist studying this site can go back in and really delve into it on their own time. So I'm going to get out of that. And we're back in Viscore or in PowerPoint here. We're very grateful. Boxfish camera research from New Zealand let us have this camera for 2 weeks to try it out. And it was just, it was stunning. So what we're working on pretty much this whole last year, and kind of, I guess, one of the silver linings of the pandemic is we spent a lot of time indoors, and that forced us to really focus on data management, which I think is an issue for all of us. And for us, the most sensible way to organize and store and display our data is using a geographic information system. And so kind of on a parallel course, working with Earth Analytics and Dr. Weatherby Dorshow, a good friend of mine who is a GIS expert, and with our own Julian Fortin in CINDAQ, we created a GIS database or GIS infrastructure, and internally here in our office, using a network access storage system and high-speed internet, a data management system. And so basically what I'm going to talk about right now is just kind of how we're working with that whole thing. And I think this is common for all of us, no matter what you're doing in underwater archaeology. We go into the field, we acquire data, we have to import that and digitize that data. We pre-process data, and we process the data, and then we publish it. And so what we've come up with is a standard operating procedure for this. And so our acquisition phase is gathering the survey data, gathering the left, right, up, down measurements. We'll use either a measuring tape or a handheld sonar, depending on the type of cave that we're in. And we collect all of this data underwater, including where we've sampled things, and any other additional documentation, whether it's photography, navigation within the cave, photographs, videos, sketches, whatever you want. All of that data acquisition happens underwater. Then we come out and we process all of that data. And so the NEMO, the survey tool that we use to measure the line, was developed by Sebastian Keister, and he has also developed Arion, which is a cave mapping tool that works seamlessly with the NEMO. So we can download all of our survey data and put it into Arion. And basically what Arion does is it provides us a bridge between our cave survey and our GIS. So that survey data gets processed with our comments in Arion, and then we're able to export it. Weatherby created an export tool for us in the Smart Cave Manager dashboard that we have. And basically we can export the cave survey data into our GIS, and we have, points, lines, and polygons for a number of different things. We have drone data where we collect up to the minute drone surface imagery. And of course, archaeology is one of the things that we do. These purple points here are all biological samples or observations that we've made. So over the last year, what we've done is we've created not only the infrastructure in GIS, but the infrastructure for all of our data. And now we're going to start really feeding that machine with data and putting everything geo-referenced on the scale, on a statewide scale here, which is pretty exciting. And of course, this allows us to easily share data with our collaborators and within our own team as well. Of course, we do a tremendous amount of public outreach as well. The 360 videos are fantastic to see on augmented reality goggles like the Oculus Go here. This is more kind of high-tech stuff here at University of California, San Diego's at the Cultural Heritage Engineering Initiative, where they have incredible technology that allows scientists to come in and go through three-dimensional models of many of the sites. This is actually the Hoyo Negro site here at Betonada, the kind of chief diver of that project, visualizing. And what's amazing here is we see things in these models that we don't see when we're actually physically there, just because, you know, we have task loading and other things that we're doing when we're underwater. So all of this technology is just absolutely fantastic, and I'm not lying when I say that I've never been more excited about what I'm doing than I am right now. And I think the motivation for all of us is, you know, there's still so much to explore here and so much to document and see and to find and discover. And I think it's not necessarily what we found in a case like the mine, it's what we still haven't found that's sitting out there waiting for us to discover. So all of our support and all of our effort is generously supported by the following individuals here and institutions. We're extremely grateful for all of their support. All of our partners across the board that have been instrumental in helping us carry out all of these studies. And of course, the National Institute of Anthropology and History and the Underwater Archaeology Subdivision. So that is about it. I'm going to just put this up here. Again, in our booth, there are some of the publications and links to all of our kind of various sites. On our YouTube channel, you can see the 360 videos and kind of there's a video that Fred put together of our kind of the discovery of the mine that gives you a little bit more in-depth behind the scenes of what that was like. So Mark, that's the end of my presentation. And again, thank you all so much for attending, and thank you, Mark, and everybody at NAS for juggling all the incredible technology to make this possible.
Thank you, Sam. I have to say, if you want to turn your camera on, we'll see you. I have to say, I think our technology management, I think, is nothing compared to yours. I mean, obviously, watching your presentation that you gave to us earlier on in the year, and then this again, I'm reminded of what Marc-André Bernier said in our 50 years of nautical archaeology, the advent of digital photography. The invention of digital photography, which of course in the early days you had photographs were a megabyte, and now of course it's how many did you say? 18,000 photos with 3.7 billion data points.
Yes,
and the computing processing power to deal with that is
I would say it's a blessing and a curse. The curse is the more data you collect, the more data you have to manage. But yeah, no, it's incredible. And it's like, I can't imagine where we're going to be 5 years from now, to be honest.
Oh yeah, absolutely. In only 5 years. You made a comment about, you know, re-looking at the dive through the eyes of the camera afterwards, whether it's the Boxfish or something else, and how you see things that you clearly can't see everything when you're underwater. Your head goes left, you miss what's on the right. Your head goes right, you miss what you can't be looking up at everything. So to be able to have that ability from the use of that technology is mighty impressive, and certainly that's some of the comments that have been made. Mighty impressive work. Can I ask about the Nemo, because I've heard of it, I've seen a box, but in terms of its use in, and obviously we know Phil Short very well, and others in that kind of cave diving community here in the UK. But in terms of how it actually works, and how would it have an application in standard underwater archaeology, not in a cave system, or is it worth an investment?
Well, from our point of view, definitely it's worth.
Well, of course, yeah.
Let me actually, I've got one right here.
Oh, he's got one. Look at that visual aid. Love a visual aid. Although he's gone. Come back.
Actually, we've got 10 of them now. So this is a Nemo here, and it's traditionally what we've done in the past is it's Cartesian photography. So it's X, Y, and Z of measuring a line, and it's depth, distance, and azimuth. And to do that by hand, there's all kinds of places where error can enter. And obviously it's very time consuming as well, and focus consuming. Whereas the Nemo, basically, there's a screen right here. There's a switch right here. That it's all through light sensors. So there's nothing coming through. It's a potted thing here. I'm going to turn it on. But basically internally here, there's a digital compass, and there is a pressure sensor for the depth and the direction. And then really the ingenious thing here, because lasers don't work all that well underwater, is there's a little capture device here. And there's a wheel that spins around, and there are two light sensors pointing down. And every time that wheel spins around, it just it knows what that distance is and calculates the distance. And so it takes a little bit of practice, but one of our projects is the resurvey of the Oshbel-Ha cave system, which again is 330,000 meters of cave. In the last 3 years, using only the Nemos, we've been able to resurvey about 150,000 meters of cave, and we've explored approximately 80,000 meters of cave as a result of that resurvey. So I don't think anybody's using it to the extent that we are.
Yeah.
We definitely are always giving Sebastian feedback on ways that we can improve how it all works, but it's great. So in terms of underwater archaeology, I think if it was a very large ship and you had to run transect lines and wanted to measure them, perhaps it would be good, but I don't know.
Yeah.
Did that answer your question?
Yeah, no, it does to some extent. I wonder about the depth calibration, and since we're used to using computers, then you put one next to the other person's and one saying one thing and one saying another thing, and then
Yep, there's a whole calibration
Yep.
for all of the sensors on it, so you can calibrate it pretty precisely. And our, just to kind of count how good this is, our measure of success when we're doing survey is it's in loop closure. So if you start and end at the same point, how far off is that closure?
Yeah.
And our biggest loop closure in Oshbel-Ha to this point is about 5,500 meter loop. And the loop closure was less than 1%, which is amazing.
I'd be happy with that.
Yeah.
Absolutely. Is your giant ground sloth the only giant ground sloth? Your new species.
Yeah, so that's part of the Hoyo Negro project, and that was discovered by the Hoyo Negro team, and that's a new species. There's actually, if I'm not mistaken, 2 new species, the Shibelbanix and the Nohochaki of ground sloth here. But in terms of prehistoric animals that we find within the caves, I'd say the ground sloth is one of the more common ones that we find. But they're Domphotheres, the small elephant, saber-toothed cats, short-faced bears, you name it, from Pleistocene megafauna and fauna within these caves.
Wow, it's amazing. Do ask questions, folks. Please use the Zoom bit because it's difficult for me to keep track of questions or comments you might put over in Feedloop. Do use the Zoom bit. What about habitation? I mean, you've got quarrying, you've got megafauna, you've got some human remains, but is that sort of burial, is it thought to be that's kind of a ritualistic place to put the dead, or is there evidence of actual living in the caves?
Yeah, that's hard to say. I think if people were living in the caves, it would have been closer to the entrance, and so there really hasn't been any purposeful excavation around an entrance of one of our cenotes or underwater caves here. It definitely would be extremely interesting to do that, and I would have to imagine that if you did, you would find evidence of human habitation, at least near the entrance. Keep in mind that there were short-faced bears and saber-toothed cats in the cave as well, so
Yeah.
it may not have been the most like wonderful place to spend a whole lot of time.
But then where else would have been safer? That's the
Well, they were roaming around the surface as well. So
yeah. Well, I think that's amazing. I got one more question from me because the audience has gone quiet. The Viscore application or software, do you know if that's being used in other archaeological contexts?
very much so. So the Cultural Heritage Engineering Initiative at the Qualcomm Institute at the University of California, San Diego, their mission is basically to digitize art, architecture, and archaeology. And so it's bringing very top-notch engineers together with artists, architects, and archaeologists to do that. So in our booth, there is a links document that I put in there with a link to the Cultural Heritage Engineering Initiative website, and I think specifically to the Hoyo Negro project, but they work all over the world, and it's unbelievable, both underwater and at the surface doing stuff. They did a wrecks in Bermuda, and there's a fly through that you can do of from kind of starting above and down into a number of different wrecks around Bermuda. So absolutely, they're using it everywhere.
Brilliant. Thank you. Right then, folks, I'm afraid we've run out of time. Sam, thank you so much for not going diving today, for giving up your day for us. Sam said he's going to hang around on the stand, on their stand over in the exhibition hall this afternoon. So if you have a particular question or want a one-to-one conversation with Sam, you can do that once I've shut this down or once Sam's got out of Zoom.